Change of state. Okay, here we are. Let's start with something nice like water. Water. Yes, here we are. It's in the liquid format. Liquid. I'm going to add heat. Add heat. And for every 4.19 kilojoules, this is 1 kilogram of water. Okay, you with me? The temperature goes up. How much? 1 degree C. Sweet! So the graph should look something like this. There's some initial temperature. Initial temp. Cool. And as I add in energy, temp, it should look something like this. 4.19 kilojoules, 1 degree Celsius more. 8.38 kilojoules, 1 degree Celsius more. That's a straight line in case you're wondering. And it should look just like this, yes? Until when? What's that? Till the boiling point. That is correct, sir. Till 100 degrees C. And then when you keep adding energy, what happens then? What happens then? What? Not quite. You have to add a boatload of more energy. But what happens to the temperature? Nothing. What's that? It levels out while you're changing state, yes? Now, it just levels out, stays right there at 100 degrees C, yes? Until it all boils off. And then if you captured the steam, then you can keep heating the steam up after that. That'd be really cool. It's kind of scary stuff, actually. This right here is what happens as the change of state occurs. Change of state occurring. Now, if you read the text, you realize occurs, whatever. You realize that it takes something like 2,260 kilojoules per kilogram to convert water to steam. All of a sudden, I'm questioning myself. I'm pretty sure it's 2,260. I'm going to look it up. Yep, 2,260. Look at me go. Bam. Say, that's a lot, Mr. Groom. That's correct. So, if I had some steam here, by the way, steam. If you see a little bit of steam coming off the pot, how many kilograms of steam do you see wafting out of your teapot in about 3 or 4 seconds? Not much. And yet, if one were to put one's hand over it, one would feel a lot of heat. Yes? Now, why is this? Here, wait, let me draw a picture. I need a picture. Teapot. No, wait, here. Face. Well, that's disgusting. I'm just going to go hand instead. Hand. I'm not sure that's any better. Nice. So I hold it over here. What happens to it? All of that steam condenses on my hand, yes? And when we say condensing, what do we really mean? When it condenses, it changes state, yes? So it changes state from gas to liquid. And in doing so, how much heat leaves the steam? 2,260 kilojoules for every kilogram. And where does that go? Into my hand, which kind of sucks. This is why it hurts a little bit. Okay? This is why if one gets burned by steam, it hurts a whale of a lot more than when one gets burned by water. Because when one gets burned by water, it simply has to cool down from the highest point it was at down to this equilibrium point because your hand's heating up as well. It's not that much. It's a lot, but it's not that much. But if you take and convert all that steam energy into your hand, wow. Then it has to go from being a gas to a liquid, and then it has to cool down after it's on your skin as well. Because then it goes, as on your skin, you're like, Jesus, now it's 100 degrees Celsius water. Now it has to cool down to this equilibrium position where my hand is. It's going to hurt a little bit. Okay, it's going to leave a mark. Nice. By the way, the other direction is going to look like this. Here's water in the middle. Oops, wait. Here's water in the middle. Whee! Here's the to steam action. Oh, by the way, they call that the latent heat of vaporization. Latent means hidden. Back in the day, the dudes were like, dude, I can check how much heat I'm putting in, and it goes up linearly like this, and then it just stops. What the heck? Well, I'd have to put more in. It's called this hidden heat of vaporization. Okay? Now, on the other end, when it goes from, obviously this is liquid to gas. On the other end, we're going from solid to liquid, yes? Is there also a same thing here? Yeah, indeed. So I have this ice cube, if you will, and I'm heating it up, and I'm heating it up. All the while it's changing state. Part of it is. Not all at one time it is. Part of it's melting, obviously. And then when it's all melted, when it's all turned to water, then it can actually start going up in temperature. Yes? And so everything down here, obviously this is the freezing point. Okay? Obviously, this is the boiling point. Okay. Yeah. So there's also a latent heat of fusion. Yeah, baby. Okay. And for water, it just happens to be, I think they use 334, right? 334? Come on, use your head. Oh, they use 335. 335 kilojoules per kilogram degrees C. Yeah, it's cool. It's cool. It's cool. Mm-hmm. Yeah, sweet. All right, let's do it, yo. Yeah. So I don't know. We can talk about that all we want. Every single substance has such a thing. For instance, if you wanted to talk about it for steel, I think it's one I have here. No, silver. I have one for silver. Check it out. The melting point, 961 degrees C. Does that shock me for silver? It doesn't shock me at all. Mr. Grimm, what is its latent heat of fusion? It is 88 kilojoules per kilogram. In other words, once you're there, it doesn't take nearly as much heat to melt it. Okay, once you're there. But it's already super duper hot. It's not like ice, which is, at 0 degrees C. You have to add quite a bit of energy to melt that. This stuff is already 961 freaking degrees. You don't have to add a whole lot more heat to get it to melt. Okay? And then at the top end, could we look at the silver turning into a liquid, to a gas? Yeah, sure. 2193 degrees C, for instance. Say, that's your boiling point. My silver is boiling. This is the melting point. Yeah. And what is the latent heat of fusion for that? Well, the latent heat of vaporization is 2335. 2335 kilojoules per kilogram degrees C. So when you have some silver steam shot onto your hand, wow. It condenses and drops 2335 kilojoules for every kilogram of steam you got on your hand. Wow. Now you've got molten, right, liquid silver on your hand at 961 degrees Celsius. No, not 961. I mean 2193. 2193, for God's sakes, degrees Celsius. And then it's got to cool down. My skin, of course, rushing up to meet it at equilibrium somewhere. Okay. It's going to leave a mark. Okay? It's going to leave a big mark on us. Okay? Literally. Yes. I don't know. That's weird. Okay? Now, here is an example problem from the homework. Right here. Cool. Ooh. Hot water enters a radiator. Hot water enters a radiator. Ooh, water, hot. Oh, you know what? Mr. Grimm's going to use the appropriate colors. Ooh, it comes into a radiator. Ooh. When I was in college, we had these radiators in our dorms. Judas Priest. It wasn't, though, hot water radiators. It was steam radiators, which is the second part of this problem. Okay. Ooh, cool. And they sucked because about 4 in the morning, they'd turn the boiler on, and those things would start banging and a clanking and a banging, and oh, geez, like someone banging on a pipe right next to your bed. Ugh, hideous. And somewhere in here, what does it do? It starts to get cold. Ooh. Somewhere in the middle, I suppose we have purple. Yes. Ooh, look at that. Yes. Nice. So, hot water coming in. Hot water in. Sorry, in. Cold water. Cold-ish water out. That's cool. And so it comes in at 70 degrees C. By the way, that's not real hot. It leaves at 40 degrees C. Now, that's not real cold. Now listen, that's interesting. If instead of doing it this way, okay, we had done it with steam. If steam had come in, it's the same radiator, just doesn't look like it, okay? You with me? Same radiator, just doesn't look like it. Steam coming in. Steam I should probably draw kind of like this, I guess. Oh, look at steam. Ooh. Turning it into liquid. Yes? Oh, now it's going to turn purple. And then probably just goes out the door as purple, to be quite honest with you. It probably never gets down to being blue, yes? No? Okay, so which is the better system? Steam or hot water? Obviously, steam is better. Obviously, steam have to come in at 100 degrees C, yes? Obviously, that's obviously. And it comes out at 80 degrees coming out this side over here. Obviously as water. By the way, still red water, I suppose, at this point, yes? So Mr. Groom, probably going to draw it up like this. In reality, it's red all the way through, right? Because it was hotter than our old hot water was, correct? Yeah. Let's talk about this for a minute. How much energy am I going to get out of this up here? Let's talk about energy content here. Okay, now let's read the rest of the problem here. 1 kilogram. So if I pump 1 kilogram of water through this thing, how much energy will I get out? Okay. So how much energy is this? I don't know. Q equals MC delta T, yes? Right? This is the amount of heat energy. So 1 liter of water, 1 kilogram, that's cool. 4.19 kilojoules and 30 degrees C. So that comes out to be like 120, 130 kilojoules, yes? Yeah. What did you get? 125.7 kilojoules for this straight hot water system, which is kind of sad. Stop it! Cool. Now listen, down here, it's got to go from being steam to water. And then it has to cool down. Then water has to cool. Well, that's cool. Check it out. I feel like the water cooling part is obviously MC delta T. Check it out. And cooling down from being water at 100 degrees C to water at 80 degrees C is this much right here. That's almost as much as I had last time in just the water system, yes? That's almost, not quite, it's 2/3 of it. Plus, we have mass times latent heat of vaporization. Now, how do I know that's my formula? Because this is in kilojoules per kilogram, yes? Not per degree C, because there is no temperature change at the change of state, yes? Latent heat of vaporization, dear. So 1 times 2260, are you with me? Is 2260. What did this one come out to be? 83.8. So when you plus them together, you get 2343.8, I think, yes? Why, Mr. Groom, that's a buttload more, roughly, than this we had up here, yeah? This is why you use steam as opposed to water. Make sense? Nice. Very nice. By the way, though, when the steam comes into contact with the very cold pipes in the morning, what happens to the pipes? They warm up, but they start to what? They start to expand. And when they do, they start bang, 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 bang in the walls, which is less than bueno. Less than bueno. Every morning, some idiots bang on the pipe right outside your wall. It's very annoying. What do you think? Not bad? Question, comment, concerns? What do you think? What do you think? What are you thinking, Cross? You good? All right, Cross, I'm going to do one more here. Then I get you guys time to work on this. A 1 kilogram block of ice, 0 degrees C, falls into a lake whose water is also 0 degrees C, and a little of it melts. Oh, boy. Oh, listen. Oh, we're going to drop. I see what we're doing. The problem is kind of stupid. Here it is. Here's the deal. I feel like I need a different color pen because it's going to irritate me. Sure. Here's this block of ice falling from the sky. Cool. What does it have right now? That's right. And what are we going to turn it into? What are we going to turn it into? Heat energy. By the way, auto shop people, this is how we stop our cars, right? Via friction, though, yes? By the way, auto two-feller. Some of those big disc brakes you're looking at today, some serious meat on those suckers, yes? There's a couple of those ones on the table yesterday. Nice. Why do you want a seriously heavy rotor on the truck? Because how much heat can it take? Well, they can get pretty hot. That's great. But the whole idea is that we'd like to be able to dissipate a lot of heat energy, yes? Because we have 1/2 mv squared of our car, and we're going to go from this speed to this speed. It's pretty much all going to go via friction. So if we have enough mass, then our brake won't change temperature as much. Yes, if we have tiny little brakes, they can heat up to ridiculously hot temperatures. They can catch on fire. I have seen that. Coming down Cabbage Hill over by, for instance, over by Pendleton, trucks coming down the hill, literally their tires catch fire sometimes. Yeah. It was funny. Driving by, I'm like, oh, that sucks. Yeah, guy's tires on fire because his bride just brakes so hard. Yeah, nice. Now, anyway, here we go. Now, it says this is a 1 kilogram block of ice. Drops in, is that what I said? Yeah. Yep, drop at 0 degrees C, falls into a lake who's also at 0 degrees C. Now, why is that important? Why is that important? Because it did not get any energy from the lake, yes? That is the only thing that could have melted it is turning the kinetic energy into friction, yes? Hitting the water? Nice. So then, here's my question. It says how much is melted? It says 0.01 kilogram melts. Okay, how much energy does it take to melt 0.01 kilogram? I don't know. Let's find out. I feel like Q is equal to M times the latent heat of fusion. So like 22.6 kilojoules, yes? Don't screw that up. Kilojoules, not joules, kilojoules. In other words, 22,600 joules. You will screw that up if you do not put that in there. Because the next thing to do is what? We need to have mgh equals 1/2 mv squared, yes? Right? Something like this, right? That's what we have. We're saying we have kinetic energy is equal to potential energy, yes? If there's no, we don't lose anything, right, on the way down. So that's cool. So what am I trying to solve for here? Well, I really don't care how fast it's traveling, do you? I don't think I do. I care about from whence it fell, yes? So mgh equals 22,600. I feel like the m is 1. I feel like g is 9.8. I feel like it fell from quite a ways up. True dat? What did you get?
2,306.
Of course, from that high, you're neglecting air resistance. There totally would be air resistance, but you know, whatever. And probably would have melted some on the way down due to air resistance, to be honest with you. But whatever, life goes on. Okay. There you go. This is why this class is a nice little primer. If you want to know all the big-time details, you take calculus with it. Ugh. And differential equations. Awesome. Now, by the way, check it out. Suppose you were driving your car and you had, let's just say, equal size rotors all the way around. Each of them had a mass of 10 kilograms. So we have 40 kilograms worth of brakes, okay? I'll buy that for a nickel. 40 kilograms worth of brakes, okay? That is the brake rotors, drums, whatever we have going on, okay? Yeah, that sounds pretty good to me. Right. So if one is traveling along in one's truck, with a really long nose on it, apparently. There we go. Oh, it's a bus. Oh, yeah, it's a bus, I guess. Good for you. The wheels on the bus go round and round. Why are you standing up while you're driving, V? I don't know. There you are. Whatever. There. Yeah. Apparently. Also, your steering wheel goes into the windshield. That's not okay. Now, listen. She's humming down the road. All the chill. Shut up! Oh, you're like mice. You're like the guy I had when I was a kid. He smoked on the bus. He was awesome. We had two bus drivers. Mike Reddish, classic, grumpy old man. He was a great guy to be. Yeah, shut up! And he would scream at you while he's smoking his cigarette, driving the bus. It was classic. And then he retired, and then this older guy, it seemed like, took over, right? And I told my grandma what his name was. She's like, oh, I went to school with him and his brother. They're twin brothers. Get this. Pearly and Pinky Gates. No joke. And Pearly Gates was my bus driver. Pearly Gates, that was my bus driver. And then the substitute was Olin Mooney. We called him the Mooner. Yeah, he was a strange dude. He had a Texas big old 10-gallon hat on. Anyway, here's Mike Reddish. Here's Mike Reddish driving the bus. We're doing we have about, I don't know, 2,000 kilograms just for a good time. And we're moving at 30 meters a second, which seems a little extreme for hauling children, but we're going to do it. Mm-hmm. Yeah, it's totally fine. It's totally fine. So let's do this. Let's come to a stop, and let's convert all kinetic energy to heat, via friction, of course. By how much do our brakes heat up? Okay, now 40 kilograms worth of brakes. They are steel. Let me just tell you right now that steel has a specific heat of, I want to say it's 0.46. Am I right? Am I right? Steel, iron, look at that. Look at me go. Steel/iron, 0.46. Okay, 0.46. That's my specific heat. So how much kinetic energy do I have here, friends? 1/2 m v squared. Yes, that's quite a lot amount. It's a lot. $900,000 joules. Yes? This is where you will screw it up. Don't screw it up. Is equal to mc delta T. But listen carefully, what is C measured in? It's 0.46 kilojoules per kilogram. Yes? So either you need to fix this into joules, or you need to fix this into kilojoules. I'm going to fix this into kilojoules. So 900 kilojoules is equal to how much mass did the brakes have? This is the other place you will screw up. You will put the bus's mass into here, and you're like, well, hardly heat it up at all. You're not heating the bus up. You're heating the brakes up. So 40 times 0.46 times delta T. The wheels on the bus go round and round, round and round, round and round. I don't know. 500? 500? 500-ish? 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 What'd you get? What'd you get?
I didn't do it right.
Well, for God's sakes. This time this is like 20-ish. No, it's like 20-ish. And 20 goes into that.
Got 40.
What? 48? Oh, 48 degrees C. Yeah, I guess I got it off by a decimal. 48 degrees C. Why, Mr. Groom? That's not even that hot at all. Well, it's not hot, though. Because if they start out 20 degrees C, now they're going to be 68 degrees C. Do not touch them. That will leave a mark on your fingers. I promise you. Okay? But that's not hot, yes? No. You watch NASCAR some weekend with the short tracks. They hit the brakes, and they're like looking, and you're like, why is his wheels glowing red? That's because the caliper that sits behind the wheels, and you can see through the spokes, is glowing red. It's glowing red because the brakes are so hot, they're glowing. Okay? Which is an issue sometimes. Because you go so fast, then the pads don't want to grip to that hot surface that good anymore. And then you're like, I don't have any brakes left. Less than bueno. Okay? So, what do we say, 48 degrees change in C? Diddly squat. You hardly know what happened. This is not stopping a semi, riding your brakes all the way down a hill, like, say, Cabbage Hill. It's like 10 miles long, and there's a drop of 3,000 feet of elevation or something. By the way, you're not really burning off kinetic energy because you're probably going the same speed all the way down the hill. You're burning off all that potential energy, yes? And so you take all that potential energy, convert it into heat energy, all right? By the way, do your brakes cool down a little bit while you're driving? A little bit. A lot? No, because how much is the air going to take off the pads, off the brake? Not much. By the way, NASCAR guys, they actually have vents that scoop air and blow it on their brakes, on their rotors. How much does that help? Not much. A little bit, but not much. In the summertime, how much will your brakes cool come down Cabbage Hill? Not at all. Okay, it looks 120 degrees today coming down the hill. Awesome. Yeah, not that it matters because they weren't going to cool down much anyways, even on a 75-degree day. No, not that much. Okay. So tomorrow we're going to have some time to work. Tomorrow we'll have some time to work on some problems from the homework. What time does this class actually get out? No, I'm done. Yeah, that's it. Sweet.